Hello, so continuing on with our Chem 1010 lecture, we are in the chapter where we're talking about the states of matter. Okay, and specifically, we're looking at changes between two states. So this could be like an initial state to a final state. Okay, well, let's say the conditions of material changes from state 1 to state 2. So specifically, we're looking at changes in pressure, volume, and temperature from this initial state to that in its final state. Okay, so that's what this chapter is about. We focus on the gas phase because it's simplest to monitor, changes in particular with the volume, with changes in temperature and pressure. Which is why we focus on the gas phase. Here's some terms to be familiar with. Okay, as we're looking at properties of the various phases of matter. Okay, one is the shape of the material. Okay. And secondly is the compressibility. Compressibility is defined as the change in the volume of a sample of matter that results from a change in the pressure. Okay. And so basically what we see is large changes in the volume as a result of changes in pressure. So that's one reason why we focus on the gas phase rather than the other two phases which are condensed. And thermal expansion is the change in the volume of a sample of matter that results from a change in the temperature of the sample. Okay. So if we looked at the various phases of matter, here's some columns here. This is the solid phase, the liquid phase, and the gas phase. So what we see here is when we're looking at these various properties, obviously solids and liquids, they have a fairly high density. Gases have a very low density. The shape of a solid is definite. The shape of the liquid and gases, to some degree, it takes on the shape of the container. The compressibility of solids and liquids are small. Compressibility of gases are large. So basically, this is easily measured. Okay, so changes in the volume are large and also moderate in gases, whereas for solids and liquid phases, they're moderate. Okay. And so because we're able to measure changes in the volume, fairly easily, that's why we focus on the gas phase. And so you'll hear this described as the gas laws. But the gas laws aren't limited to just gases, but can be extended to solids and liquids as well. The only thing is that with solids and liquids, because they're condensed phases, there are attractive forces and repulsive forces that should be taken into account because the molecules feel each other, they touch each other when they're in those states, and which I'll show in a picture briefly. So for example, this is a solid phase here. We can see the molecules here are definitely in contact with each other, so there are attractive and repulsive forces that take into account. If you look here with the here's my mouse pointer showing the liquid phases, liquid molecules. They're touching each other right here. In the gas phase right here, the molecules only touch each other momentarily, and so the attractive forces, repulsive forces are very small, and so that basically makes the gas phase much simpler to analyze, and basically we can take this analysis and extend it to the other two phases. We won't talk about the equations of state for solids and liquids for this in this class, simply because the equation is actually more complex to do that. But we will focus on the gas phase. Okay, and so this gas phase equations follow the kinetic theory of matter. Okay, so there are 5 postulates of the theory. One is matter is made up of tiny particles, the molecules. Particles of matter are in constant motion and therefore possess kinetic energy. Now this is fairly important right here, in that because the motion is associated with kinetic energy is actually associated with temperature. So temperature is a way to measure the kinetic energy of the molecules. So you could see temperature as a molecular speedometer, if you will. Postulate 3, the molecules possess potential energy as a result of those molecules repelling or attracting each other. Actually, in the gas phase, this is fairly small here. So at least this part of the equation, this is what simplifies the equations for the gas phase. The equations for a state for gases are much simpler than those for liquids and solids. Okay, and then the average particle speed increases with the temperature. So basically, as temperature rises, then basically we have an increase in the kinetic energy. And then also the 5th postulate here, particles transfer energy from one to another during collisions in which there's no net energy lost from the system. In other words, the transfer of energy is elastic. There's no energy that's lost. And so these are the assumptions of the postulates of the theory and the gas laws. Okay. One thing that's implicitly mentioned here is that with speed, the velocity of molecules, at absolute zero, the speed or the velocity is 0. Okay, so basically, absolute 0 temperature corresponds to 0 kinetic energy. Okay, and so you cannot have something. It's impossible to have temperature that's below 0 that we've talked about earlier in the semester, and so that is why when we do calculations with gas laws dealing with temperature, we must use the Kelvin scale. The Kelvin scale is important because at 0 Kelvin we have 0 motion of the molecules and basically zero kinetic energy. And so that's also part of this kinetic this kinetic molecular theory of matter. Okay. And then right here, as we can see, solids, you can see in this GIF file, there's a little movement in the solid. Liquids, there's a little bit more movement, and then in the gas phase here, there's even more movement. So basically, you can see that there's more energy involved in here, where molecules move around a lot more so, and actually the motion of the molecules, you can see there's a direct relationship with the temperature. The greater the kinetic energy, the greater the temperature. But you can see that there's also an effect with pressure and volume as well. Pressure being a unit of measurement of force per unit area, and then the volume is basically a result of the pressure that's being pushed out. Okay. All right. So basically, we'll focus on the gas laws. Gas laws are basically mathematical expressions that describe the observed behavior of gases, when they're mixed or subjected to pressure or temperature changes or allowed to diffuse. And so right here, when we're talking about subjecting the gases to pressure or temperature changes, we're focusing on what we know as Boyle's law, Charles' law, and the Gay-Lussac law, okay, which we'll cover in a moment. And diffusion here is another thing that gases do. And so with diffusion, there's another set of laws known as Graham's laws. Okay. So basically, what the equations that we'll talk about have to do with being able to predict whatever changes that occurs in the pressure, volume, and temperature as we go from some initial state to some final state here. Okay. All right. Now, one thing that one common example of an equation of state. So basically, there's a name for these equations. It's an equation of state. Okay. Now, when you're measuring temperature, let's say using a thermometer here, so what happens here is that you're taking advantage of an equation of state relationship. So if we take these materials and then heat it like so, say we heat the material. Okay, what happens here? Basically, what happens here is that the volume expands. There's an expansion of volume of, let's say the mercury in a thermometer. So this increases as a function of heat, and so basically this provides a way of relating the volume. Okay, the volume is a function of the temperature for this equation of state. So really, we're not measuring the we're not measuring temperature directly, because that's somewhat difficult to see. What we rely on is basically observing changes in the volume, which is easily observable. Okay, and so from looking at changes in the volume, we know the temperature. Okay, and when we know the temperature, we have a way of relating this with the kinetic energy of the matter. Okay. Similarly, when we measure changes in the pressure, obviously pressure is basically a force per unit area. That's something that's difficult to see, but what we can see is we can measure changes in the volume. So if you look at this, is a diagram of a barometer here. So this is a mercury source. This is the atmospheric pressure. The atmospheric pressure pushes against this column of mercury, and then basically it goes up this column. So changes in height correspond to the pressure. So basically, the higher the pressure, the greater the volume will expand, and greater. So that's how we measure pressure. So, and then again, what we do here, just like in measuring temperature, we rely on an equation of state to do this, to help us make this measurement. Okay. And so pressure here is a force that pushes against a unit a unit area. Okay, and so the SI unit for pressure is pascals. But a very common thing that we use here in the English system, which is torr. Okay, so torr. Okay, 1 torr basically corresponds to a 1 millimeter height of mercury. Okay, that's raised in this barometer. Okay, so if you look at this picture right here, you'll see the heights in millimeters. That's millimeters of mercury corresponds to a torr. Okay, and then the actual pressure that we're breathing, at sea level, is 760 torr. So basically, the pressure that we're accustomed to is 760 torr. And this is the same thing as 1 atmosphere. Okay, so what I'm doing is I'm writing an equivalent statement here, comparing torr with atmosphere. Okay, and so that is what's known as the standard atmospheric pressure. So 760 millimeters of mercury, or 760 torr, or 1 atmosphere, they all mean the same thing. Okay? And on planet Earth, we consider that to be the standard pressure, okay, by which to base our measurements. And then so 1 torr pressure here is the pressure needed to support 1 millimeter column mercury in a barometer and basically that's a standard atmosphere, a standard atmospheric pressure. Okay, so that's basically our baseline for measuring pressure. Temperature, the baseline for that is 0 Kelvin. Okay, that's where we have no motion, where all motion stops. Okay, so if you recall this picture here, even with solids, there's some motion there, so it's not absolute zero, but basically when it's 0, that's 0 Kelvin. That's the scale that we use for temperature. The scale that we the standard pressure here would be 1 atmosphere. Okay, and so here's some conversion factors here, so equivalent statement. And so just to warn you, to give you a heads up when I come back from my trip from Memphis, we'll have a clicker question on this. So hopefully this skill is something that you've not lost from the earlier material in the semester. Okay. And so also this is just a point to remind you here, is that there's no such temperature as a temperature that's below absolute zero. Okay, so in the Kelvin scale, that temperature is 0 Kelvin. Okay, that's easy to remember. For the Celsius scale, that's minus 273. For the Fahrenheit scale, it's minus 459. But in the case of solving gas laws, and especially when you're dividing and multiplying numbers, we will not use the Fahrenheit or Celsius scale. We'll basically, because if you do so, you'll get an incorrect answer. The way to get correct answers is basically to follow to convert into the Kelvin scale. Okay, and so that's just an important point to remember. Okay, so let's talk about these laws one by one. Okay, we'll talk about Boyle's law, Charles' law, and Gay-Lussac's law. Okay. Now we talk about these observations. In terms of problem solving, there's really only one equation that you really need to know. So it's not necessary to memorize all of these 3 separate equations. We can basically combine all of these expressions into a single equation that for you to know, and so there's no need to memorize each of this, but we can talk about what these equations describe. Now, basically, remember we're talking about a pressure, volume, temperature of, let's say, of one state. Compare that with another state. Sometimes like this subscript 1 here refers to like an initial state. Subscript 2 refers to a final state. And this may also be written as, let's say, Pi VI over is equal to PF VF. So there are different ways of writing that, but the point is that these are 2 different states. Okay, and these are the same states. So this is one state here. This is a second state. The constants here correspond to what variable is held constant while you're looking at these other changes. Okay, so let's look at Boyle's law. Boyle's law basically explains that there is a difference, explains the trend of a difference in pressure versus volume. Okay. So, for instance, if you were to take a balloon, and apply pressure to it, so here's a illustration here. Here's like a balloon here, and then there's an external pressure that's applied to it, like so. Okay, what happens to the balloon? Well, basically, it'll get smaller, as a result. And so what we see is as pressure increases, the volume decreases, like so. Or another way to write that is that pressure is inversely proportional to the volume. So, this means that as this gets high, let's see, maybe we can write it like this: 1 over P is equal to V. So, for example, if P gets large, let's see, if P gets larger, you'd see like 1 over P, then V will get smaller. And that's exactly what we observed here. Okay. And conversely, if P is small, then the volume, will be greater. Okay. So, so a way to write that, so instead of getting rid of, let's say if we want to write this in terms of a constant here, that would be the same thing as P equals KV. So where K is a constant value, so we can replace the proportionality with an equal sign. Or another way we can write it like this. We can write PV, see 1 over PV is equal to K, like that. So that's a constant. Or we can do an inverse. We can say we can say PV equals 1 over K. I mean, that's also a constant as well, but anyway, this is a constant value that might be more easily written like so. PV equals, I'm just so that you can get rid of this fraction. But this is like 1 over a constant is a constant. Okay. So we can say PV equals some constant value. Okay. All right. And so if we have now if we have one like an initial state like this, okay, and then if we have a final state, okay, that's also equal to a constant, okay, and so so basically that means that if we have like the product of the pressure and volume will equal basically the same constant, even if you change this. Okay. So another way to write it is like this. Okay, and so that's basically an expression of Boyle's law right there. Okay. P1 V1 or P. It's actually written both ways. You can. Okay, it just means state 1, state 2, or initial state or final state. Okay, it's basically the same thing. Okay, so that's what we see for Boyle's law. Okay. All right, so that's Boyle's law. Now Charles' law is basically describes something that describes the volume of the gases as a function of the temperature. Okay. So if we look at the volume of something here, the volume, and let's say we heat it up, say this gets hot. Okay, what we observe is that the volume expands. Okay, so it gets larger. Okay, so what's happening here is that if you think about this, if you think about the temperature being a molecular speedometer here. So right here, if we're heating up this gas here, we're basically what we're doing to the pressure. We're increasing the speed of the gases here, and as a result, we're increasing the force that's applied per unit area. So the pressure increases, and the pressure puts us against the walls of the walls of the balloon, if you will, and so you'll get a larger pressure. Yeah, like so. So that explains this. Okay, and so what we see is that as we increase the temperature, there's a direct increase in the volume. Okay, so unlike pressure volume, this is a direct relationship. Okay. Now, in the other case where we have PV where we had this inverse relationship right here. Okay, this is known as an inverse relationship. Okay. So from experimental results, you see this is an inverse relationship. This is a direct relationship. Okay. So that's something that we observe. That's something that we observed. That's described by Charles' law. Okay, and then yeah, right. And so okay, so if we wanted to right. So if we wanted to do this here, we can write this as a constant here. I suppose we could, in keeping with the equation that's on the chart there, we can say volume is equal to some constant times temperature, like so. So we can say V over T is equal to some constant, right? Okay, and then so if we were comparing the volume and temperature between two states, so let's say this is an initial state here. We can rearrange it like so. We can have something else like a volume and temperature like so, and then basically what we can do is if we note that this is true, okay, some constant there, constant K, so basically we can set these two equal to each other. Okay, V1 T1 is equal to V2 V over T2 because they're both equal to the constant right there. Okay, so if I rewrite this, okay, so if I rewrite this, this is what I get. So we get V1 T1 is equal to V2 T2. Okay. Or in other words, we can say VI TI or TF VF or TF. Okay. So this is basically initial state here. That's a final state. Okay. And so that's Charles' law. Okay. And then the Gay-Lussac law. Okay. The Gay-Lussac law basically similarly just says that there is a direct relationship between the pressure and the temperature here. So again, what we see here is that if we increase the temperature increase, okay, so there's a volume increase. Volume increase because there's greater pressure right there. Okay, and so we can so P1 is proportional to T1. Okay, what we can do is replace the proportional sign with the equal sign for this reason, and if we have P1 equals KT1 and P2 equals KT2. Okay, so what we see is that if we solve for the constant K, so K equals P1 T1, K is equal to P2 T2, like that. So we can basically set these equal to each other. So it's like saying P1 T1 is equal to P2 T2. Okay, or you can write it like this: Pi
Ti is equal to Pf Tf. Okay, so that's where, so this is, okay, so this is the Gay-Lussac law right there. Okay, so that's the last one down here. Okay, so that's the Gay-Lussac law. Okay, so and these laws are based upon experimental observations between changes of pressure, volume, and temperature from one state, comparing from one state to another state, next state. Okay. All right. Now, instead of let's say memorizing these three equations, we can basically have a combined gas law that explains all three. Okay, so what does that look like? Okay, so it looks like this. Looks like this. So P, Pi Vi over Ti is equal to Pf Vf over Tf. Okay, so you can see that there, intuitively, you can see how that's combined. So I won't go through the derivation of all of this, but you can see some parts here, right here. So we see aspects of the Boyle's law right here. Okay, we see aspects of the Gay-Lussac law right there, Gay-Lussac law, and then Charles' law from this Vt over Vt, just like that. So all you have to do is just know this single equation. You don't have to remember all three of these, but this is the combined gas law. All right, so that's the combined gas law right there. All right, so let's go ahead and talk about how this is used. Okay, so that's Boyle's law. Okay, so that's how we came up with the P1V1 or PI-VI is equal to PF-VF. Okay, and then this is the Charles law here. So this is how we can come up with VI-TI is equal to VF or TF. Okay, so here's another experiment that underscores this point here. So you can see if you take a balloon here, you put it in liquid nitrogen, so the gas is still there, but you can see that it's compressed, quite a bit right there. We can take it out of the dewar. So, but the gas is still there. So this is an example of Charles' law. Okay, and then we can combine all three laws here to get the combined gas law as shown in this PowerPoint slide. Okay, so let's use this. Okay, so here's a question. Here's a problem here. Right there, right? So if you read the question, this says a gas sample has a volume of 2.50 liters when it is at a temperature of 30 degrees C and a pressure of 1.80 atmospheres. What volume in liters will the sample have if the pressure is increased to 3 atmospheres and the temperature, is increased to 100 degrees C? Okay. So basically, this is a combined gas law question. Okay. Basically compares. You're asked what happens when you go from one state to another state here, and how would you solve for that? Okay. Well, one thing that might be useful, okay, is to create a table of values, and so basically you can see what's done here. This is a PVT for the initial conditions. This is a PVT for the final conditions here. So if you read the question here, this is the first condition, okay, where you have 1 atmosphere and then a volume of liters, and then you have a temperature. Now notice what we've done here. We can't use Celsius. We have to convert this to Kelvin, because Kelvin is the absolute scale, where 0 signifies 0 kinetic energy, and on up. And so right here we have the final conditions here. We have a pressure as 3 atmospheres here, and then we have
the temperature is 373 Kelvin, like that. Okay, and so you can see that what we have here is that the question is asking for what is the volume in liters. So we're asked what is the final volume, V sub F. Okay, so we know. So the way the question's asked, we're basically given one unknown, and we know all the other variables. So that means that we just have to rearrange the equation to solve for that unknown. Okay.
So right here, that's exactly what we're doing. So so most of this is just algebra. Actually, all of it is algebra. But so what we're doing is we're solving for V sub F, just like that. Okay. So we can see how would we do that. So I guess we could just put this on the left-hand side of the equation like so. Just switch the sides. Okay, over T sub I, and then what we can do is we can multiply both sides by T sub F. Okay, so if you do that, it's like saying this. Okay, so multiplying both sides by multiplying both sides by T sub F. So if we do that, we multiply this, by T sub F. So basically that cancels out just like so. Okay, and you can get rid of this. So the equation looks like that. Okay, and then lastly, what do? We can divide both sides by V sub F. So the equation looks like that. So this obviously one. I'm sorry. So we don't want to. Sorry, I got ahead of myself. Not V sub F, but P sub F. Excuse me. So that's a mistake. P sub F. Okay. So you can see that the P sub F drops off like that, and it stays here. So we're left with the equation dealing with the V sub F, just like that. Okay, so we have V sub F, just like that. Okay, so that's the rearranged combined gas law equation, just like that. All right. And so what we would do here is we'd substitute the various values from the table values here into these these variables in the equation, and this is how it's done. Okay, so this is V sub F is the unknown here. V sub F is the unknown, and you can see that we have so that's the same equation that I've sketched out on the board, on the marker board. So we have P sub I, V sub I, T sub F. So what number goes here? This is the P sub I. That the volume goes there. Okay, and then the final temperature. That's this one right here. That goes right there. Okay. So and you can see it on the bottom as well. And then in the denominator we have the initial temperature here, which is that, and the final pressure, which is that. And so you can see these go into the denominator. You see these familiar numbers there. If we do the calculation, we come up with 1.85 liters. Okay, so that is the final volume from that calculation. Now, and so that's basically if we're given all the variables. Now, a lot of times, what we can do is that we can actually simplify. I mean, if you read the question, well enough, we can get to each of these individual equations, the Boyle's law, Charles' law, and Gay-Lussac's law, by basically noticing. If we notice that a variable is held constant, so a temperature that's held constant, a pressure that's held constant, or volume is held constant, what will happen is that those corresponding variables in the combined gas law will basically cancel each other out, and then you'll get these simplified equations. So that's another reason why You just need to know the combined gas law, and then from that you'll get the individual laws. Okay. So for instance, suppose, let's say you're asked PV over T, PVF over T sub F, like that. Okay, so suppose you're looking at the pressure, volume, temperature changes like in a gas cylinder. Okay, so this is a gas cylinder. So let's say the gas is pressurized here. Okay, maybe you're increasing the temperature here, and then you're also increasing the pressure. So what is held constant in this particular case? What's the same here? So if we're using the same cylinder, and all we're doing is we're just changing the pressure and temperature here. Obviously, the thing that's the same is the volume. The volume's identical. Okay, so in this particular case, this would the combined gas law would simplify to the Gay-Lussac law, as we can see here on the bottom. So that's the Gay-Lussac law. That's what you get. If you read a question, and basically you can notice that some things are constant. Okay. By the way, what is the easiest variable to hold constant that takes not minimal equipment? Okay, what's the easiest variable? What would you say? Well, I'd say pressure. Okay, so let's say this is probably the easiest thing to control. Okay, so let's say if you have a beaker, right? A beaker or some container, obviously this is exposed to atmosphere, to air, but then suppose you have a collection of gases that are here, whatever. Whatever. So in this particular case, the pressure is constant. Pressure is constant. So we have V1 over T1. Or PI, VI, TI, PF, VF over TF. Okay. And so let's say that the gas happens to be very dense. Okay, it falls to the bottom of the beaker, but otherwise, they're there. So what we can see is that the pressures, the external pressure, is the same. So in this case, like the P's will drop out, like that, and so because they cancel each other out, if the pressure's the same, and so that would be like Charles' law right there. Okay, so that's just an example of how this combined gas law can simplify to those individual laws. I think a lot of folks just find it easier just to look at the combined gas law and just work with that. And if there are extra variables, then you can cancel as needed. Okay. So just to alert you, I will have a clicker question based on the use of the combined gas law, and basically we will cancel out one of the variables. You should be able to cancel out one of the variables. So that's just something to keep in mind in our next lecture when I come back. Okay. Now, so that's the combined gas law right there. Okay. All right. Now, here is an example. Here's another example here of okay, and then we've done this example here. Here's an example. Here's that example where we've calculated 1.85 liters based on this question, just like that. So just review this question here, and then actually the clicker question will actually be simpler than this one because you can cancel something out. Okay, so you'll see that when I get back to class. Okay. So now Now what I want to talk about is the ideal gas law. Okay, so the ideal gas law, okay, is PV is equal to nRT. Okay, all right. Okay. By the way, if you notice this, okay, nR, okay, actually that's a constant. That's considered to be a constant. Where let's say R is the universal gas constant. Okay, and then N is the number of moles of gas. Okay, that's present. Now, one thing to note is that I mean, there's some problems, some advanced problems, where the number of moles of material do change, but for problems that we'll talk about in this class, they will not change. So basically, if we're looking at a collection of molecules as we go from one state to another state, the number of molecules, the number of moles will remain the same. So basically, this is part of the constant that we've talked about previously. So we see the PV over T is equal to some constant. Basically, this constant is basically nR, part of that. But it's useful to more specifically describe this constant, as it can tell us more things. Now, one very neat property of, let's say, the ideal gas law, one of the things that we can determine is the molecular weight of an unknown compound, or unknown species, if it's in the gas phase. So if we know the pressure, volume, and temperature of any substance that's in the gas phase, and we're able to measure its mass, well, basically we have a way of determining its molecular weight. That's one thing that is interesting about the ideal gas law. And note that Avogadro's law, equal volumes of gases measured at the same temperature and pressure contain equal numbers of molecules. Basically, this principle is what allows us to be able to determine the molecular weight of any compound if it's in the gas phase. So we know that if we have 1 mole of any compound, doesn't matter what the compound is or what the material is, could be oxygen gas, could be methane gas, propane gas, anything. If we know that we have 1 mole of it, that is, if we have 6.02 times 10 to the 3 molecules of it, it will always occupy 242.4 liters at standard temperature and pressure, meaning pressure at 1 atmosphere and at 0 Kelvin. So we know that that's always true, no matter what the identity of the material is. If it's in the gas phase, that's true. Okay. So I want to make some further explanation about the ideal gas law. This is the ideal gas law that I drew on the marker board. The R is a particular number, particular constant, so it is this, 0.0821 liters atmospheres per mole per Kelvin. Okay, so that is the universal gas constant. Okay, and also remember, when doing these calculations, in order for the answers to make sense, the units must cancel out. This happens to be the units for the gas constant. But if you have, let's say, a volume that's like cubic centimeters or cubic inches or something like that, or some English unit, in order to cancel out when you're doing this calculation, make sure that you convert that into liters, right there, so that they will cancel out appropriately. Or if you have a pressure that's in pressure in atmospheres or something, or pressure in pascals. If you're going to use this constant, if you want to get those units to cancel, this also has to be converted to the appropriate units, atmosphere, so that you can cancel that out. Okay. And of course, temperature here is always in units of Kelvin to solve for these types of problems. Ideal gases versus real gases. Okay. When I say the ideal gas law, does that mean, am I saying that that's an imaginary? No. I mean, they exist in reality. Okay. And now, real gases deviate from behavior by the gas laws, but under ordinary conditions, these deviations are small. Okay, so why is that? Basically, the reason is because under ordinary conditions, the repulsive forces, the attractive forces will be very minimal, very minimal. However, if you have like unusually high pressures, so if you have, let's say, thousands of atmospheres or something, you will get some attractive forces. Because when you're having that kind of pressure, you're forcing the molecules together. They'll see each other, and therefore you'll have interparticular attractions and repulsions. Okay. And so so because it's small, gas laws can be used for a lot of real gases. Just as long as they're small. But if there are intermolecular attractions, it will deviate from the simple law that we have mentioned already. So, namely this, it'll deviate, under those conditions. And of course, the reason why it works best for single atoms or nonpolar molecules is because these types of atoms or molecules feel the least amount of attraction. There's less intermolecular interactions, and therefore, it's most accurate from that. Okay. So this is this is basically one of the equations you should also know. Okay, for exam purposes. Okay, so let's look at a question. Okay. So here's how the question reads. This is an ideal gas law question. Okay, so combined gas law questions basically deal only with pressure, volume, temperature changes from one state to another. Okay, if you have let's say the number of moles that's involved, moles of gases, that number is given, or if you have a mass, that's also part of the problem. Okay, that's an ideal gas law type calculation. Combined gas law calculations only involve pressure, volume, temperature, but then if you involve amount of material, that's an ideal gas law calculation. Okay. So here's the question. Okay, a 2.50 mole sample of gas is confined in a 6.17 liter tank at a temperature of 28 degrees C. What is the pressure of the gas in atmospheres? So basically, how do you solve for that? Solve this question. So the question is asking for what is the pressure of gas in atmospheres. So that means that you just need to rearrange the ideal gas law. So for this type of question here, P is equal to nRT over V, just like that. Okay, so you just need to determine, what the appropriate values are. So if we know that we have the number of moles 2.50 moles. Okay, like that. R is gas constant. That will be the same. The volume here, we're told that it's 6.17 liters. For the temperature is 28.0 C plus 273, so that makes it 301 Kelvin, 301 Kelvin. Okay, so basically we just take these numbers right here, okay, and then substitute them into the equation, and then we can determine our answer, like so. Okay, so that's what we get here. And this, if we look at the screen,
So we multiply 2.50 times the gas constant, and then the temperature, and then 6.17 liters. You can see, well, look at how these cancel out. So basically the kelvins, they cancel out here and here. Okay, the liters, they cancel out here and here. The moles cancel out here and here. So basically the only units that we're left with is atmospheres. And it turns out to be, if you solve this mathematically, you'll get 10.0 atmospheres. And so that's the answer to this question. What is the pressure of the gas? Answer, 10.0 atmospheres. So that's one useful solution you can get from using an ideal gas law. Okay. So remember that question that I had mentioned earlier? So one thing that's really neat about the ideal gas law is that it will allow you to determine a molecular weight or formula weight of an unknown material. If you know it's the gas phase, you know that it'll definitely have certain behaviors, and that allows us to calculate the formula weight. Okay. So in this type of question, okay, what do you need to do? What do you need to do? Well, so here we have we know that we have 4.00 grams of the sample of gas. Okay, we know that it exerts this type of pressure when confined into a container that has this volume, and then we know that temperature. Okay, so to solve for this, we know the mass. Okay, and then we know if we know the mass of this, and we know the volume. Let's see. If we know the mass, and we're able to figure out the number of moles. Okay. If we know the mass, we are able to figure out the number of moles. We should be able to figure out the molecular weight. Okay, because the moles is part of the ideal gas law. Okay, and so remember this equation. This is trusty equation. Okay, mass over formula weight is equal to moles. Okay, so basically, if we know the mass, that's given the problem, and then we know the number of moles, then we can determine the formula weight, just like that. So this would be the unknown right here that we can determine. Okay. So let's go ahead and do this. Okay. So we have PV is equal to nRT. Okay. So we're told the pressure. We're told the volume. Okay. We're not told the number of moles. So this is an unknown. And we're told the temperature, so we should be able to figure out the number of moles. Okay, and from the number of moles and the mass, we should figure out the formula weight of that unknown gas. Okay, so let's do this. Okay, so nRT is equal to PV, like that. Divide both sides by RT. So this is like saying N is equal to PV over RT, okay, just like that. And so that's how you determine the number of moles. Once we determine the number of moles, then we can use this and determine the formula weight. Okay, so let's do that. Okay, so let's determine the number of moles that's available. So what you do here is that you put in the value for the pressure, the volume, and then the temperature. Okay. So reading this question, what do we see here? Okay. Reading this question, we see the pressure is 1.71 atmospheres. We see the volume is 3.60 liters, and the temperature is 27 degrees. But remember, we need to add 273 to this number. Okay. So that's what we need to do. Okay, so
So what we see is pressure 1.71 atmospheres. Okay, volume is 3.60 liters, and then temperature is 27 degrees C plus 273, which is 300 Kelvin. Okay, so these are the heat numbers here. 1.71 atmospheres, 3.6 liters, and then 300 Kelvin. So what you do here is to plug these numbers in. Like so, you can see there's the pressure, volume, gas constant, temperature, and you can see how the units conveniently cancel. So the atmospheres, they cancel, the liters, they cancel, kelvins, they cancel. So we're left with 1 over moles, and so the answer is 2.50 moles. Okay, so that's the number of moles. Okay, and so the molecular weight, mass over formula weight, is equal to moles. Okay, or in other words, we can say this: formula weight is equal to mass over the number of moles. Okay, so basically that's just an algebraic rearrangement of this equation, top equation, to this equation right here. And so that's what we see. So we have, as part of our solution here, this number is given. That's the mass that's given in the question. Okay, and then we know we have 0.250 moles of it. So if we do this arithmetic, we get 16 grams per mole. So that's the molecular weight of the gas. So so it can be methane with carbon that has, methane is CH4. Okay, so carbon has 12, and then you got 4 of those. 12 plus 4 is 16. It could also be like perhaps an oxygen radical or some other gas. But anyway, this is something that's a piece of the puzzle that can be used. Okay. So that's what I've got to say for now with the ideal gas laws. Okay. So next time we come back, there'll be some clicker questions. So be ready for that.